Alright, so here's another go at beer and homework. So the question that I've gotten a few requests for is number 3 on the thermo homework, which is the stators in a gas turbine are designed to increase the kinetic energy of the gas passing through them adiabatically. Air enters a set of nozzles at for this question, 400 psia and 820 degrees Fahrenheit, and at a velocity of 91 feet per second, and exits at 350 psia and 525 degrees Fahrenheit. What we need to do is find the velocity at the exit. Now, as per my usual, I'm going to go ahead and write down all of our variables just because I like to be organized. So I've got velocity 1, which is the 91 feet per second, the temperature 1, 820 degrees Fahrenheit, which is 1280.67 Rankins. I just do that anyway because it just makes some things a lot easier, especially in fluids when you have to do a lot of Rankins. Pressure is all lined up and I got that ready to go. Now the equation that I like to use, especially for these, it seems the most straightforward to me, is the steady flow energy relation. So you've got the enthalpy plus the velocity squared over 2 plus your Q is going to equal your enthalpy 2 plus your velocity 2 squared over 2 plus your work. Now, a little thing to note, and she didn't really note this in class really well, is that this is an adiabatic system. So your Q and your work, so your energy that's being released or the energy that's being put in is automatically 0 because it's an adiabatic system. Now where this gets tricky is we've got to find your enthalpies for this because we've got the velocities. We're trying to find V2. We can go from here pretty easy, but we've got to go to the tables. So my suggestion is when you're looking at the tables for this is to go with the pressures. So we're going to start with the 350 because that's the easier one to do. And so you're going to go to the superheated water. Anything where you're dealing with water over 210 degrees Fahrenheit or 100 degrees Celsius is going to be classified as superheated. So I'm going to be looking at pressure tables for superheated water under these conditions. So we've got 350. All right, so come over here. We've got our 350 psia, which is another thing we have to worry about because on some they do English units, some do metric units. And because I have Google, I didn't really want to futz with doing any kind of conversions from this to an SI to whatever. So I just found an appendix and I found them in English units. So we start out and what we want is 525 degrees, but what we are most readily given is 500 degrees Fahrenheit has a enthalpy of 1251.9 BTUs per pound. And as you go down, you're like, oh crap, there's no 525. So what you're essentially going to do is you're going to do 550. So you're going to take the 550 and the 500, your two enthalpy values, and you're going to average them. And if you don't know how to average now, well, you're kind of screwed. But you've got, for the average for your H2 is going to be 1267.05. That is right at 525. So that'll be your answer for that one. So you've got your H2. Now we're going to move on to your H1, which is a little bit trickier because they've got 820 for your temperature. So what you're going to look over here at is we're going to come down. We're looking, all right, we've got the 300, we've got the 400 psia. Look at the temperature. We've got 8 and 900. So if you're looking at your enthalpy values, and you're just kind of glancing at them, you notice that they don't increase dramatically. It's 1417 to 1470 over 100-degree difference. So all that I decided to do was I started at I started averaging 800 and 900, and that will give me the temperature at 850 degrees, which is 1443. And then halfway in between, the median between 850 and 800 is going to be 825. So if you average those two together, you're going to end up getting 1430. It's good enough for me, 1425. It's 5 degrees off. You'll notice as you go through the tables, there's not a huge amount of change, and we do get, yeah, I think it's like 2 or 3% give or take. So, you know, in physics, it's called a margin of error. You know, you got it to a magnitude of 10, you're fine. And for this, I mean, we're fine with 525, I think. So, I mean, if you wanted to do it again, you could do a 525 and an 800, and that would put you in the middle, like 514 and a half, and then you could average those and just keep going. But, I mean, I'm drinking and I'm doing homework. I'm gonna try and just get close enough. So that eventually gave me 1430.35 BTUs over pounds. And now it gets really pretty easy. You just got to do some math stuffs. So we've done all of our conversions. We've done everything we need. So all we have to do now is the plug and chug method. And because it's been a minute, let's pull back up and we're like, so what equation are we getting all these for? Don't forget we're doing the relation, the steady flow energy relation. So we're going to be using this, once again, adiabatic system, so you automatically cancel out your Q and your W because you don't really need them. You're just going to plug and chug down here. And one thing that messed me up the first time I did this problem is you've got to do a BTU conversion. So 1 BTU per every, 25,037 feet squared per second squared unit, ridiculousness. So, you just go down through here. This is the way that I solved it. It made the most sense to me. It could make sense to you. I don't know. But then you end up getting your V2 down here is eventually 2,861.01 feet per second. And that is when I did this problem on my own the first time with my numbers. That's pretty similar to what I got, though the pressure for this problem is way greater than mine was. So I hope that helped, and I'm gonna keep drinking and doing homework. So yeah.